This video is on the objective make a conclusion and interpret the results of a one-mean hypothesis test. Now this is with the population standard deviation known, right? Sigma is known, so that means our test statistic will be a z-score, and this time we're using the p-value approach. Right, so remember there's the critical value approach, where you find critical values and set up a rejection region, and then see if your test statistic falls in that rejection region. The p-value approach is where you find the test statistic and then you find that particular test statistic's p-value. And I'll talk about how to find that. All right, and this is number 1, so it's the first video on a question related to this objective that I'm seeing in your Newton Alta homework. So let's take a look. All right, so again, if you want to see more about this, please click on more instruction. Look at their videos, their notes, their examples, and hopefully that helps you. All right. So we're seeing here, Rachel, a city employee, would like to make the claim. Right, always starting with some claim or belief or statement. She'd like to make the claim that the average amount that residents spend per month on public transit fare is less than $140. Rachel samples 25 city residents and obtains a sample mean of $125.80 spent per month on public transit. At the 5% significance level, should Rachel reject or fail to reject the null hypothesis given the sample data below? All right, so I'm going to write this stuff out myself. Okay, how was all this stuff found? Yeah. So I'll pull up a piece of paper here. And remember, the way a hypothesis test always starts is with a claim or some statement that is to be tested, and it's a claim about a population parameter. In this case, a population mean. So I'm going to let mu here. They mentioned the word average, right? So a mean. I'm going to let mu be the average amount that residents spend per month on public transit. I'll just say it's the average or the mean amount spent per month on public transit for these residents of a town. And this is for all residents, right? This is the population mean. Right. And the claim, she said she would like to make the claim that the average amount that residents spend per month on public transit fare is less than $140. Right, is less than. Then from the claim, once a claim is made about a population parameter, then the hypotheses are set up. You have your null hypothesis, which was H sub 0, and your alternative hypothesis, H sub A or H sub 1, depending on what videos you're looking at or books you're looking at. The claim did not involve equality. Right? Mu is less than 140, so the claim will be represented by the alternative hypothesis. All right, and then the null and alternative hypothesis should be opposing statements. So if the alternative hypothesis is that the mean is less than 140, the null hypothesis would be that the mean is greater than or equal to 140. But in this book, right, in the Newton Alta website, instead of writing what it really is, they're just going to write what you're going to be assuming to be true, which is the equal part. So if that's the null hypothesis, they might just represent the null. They will just represent the null hypothesis this way, with what we're going to be assuming. We're going to be assuming that the mean, the average amount spent per month on public transit is $140. And this, this mu equals 140 will most likely be written as the null hypothesis. Okay. Then after the claim is set up and the hypotheses are written, you identify a significance level for the test. Significance. Now that was that value alpha. Now if the significance level is not mentioned, we can assume 5%. That's usually a reasonable significance level for any test. But it is mentioned here. They said it was 5%, right? They said at the 5% significance level. So 5% or 0.05. All right. Then once the significance level is identified, a sample is taken, or samples, but in this case it's just one sample. A sample is taken from the population, and it said that Rachel sampled 25 city residents, right? So the size of her sample, which is N, is 25. And she obtained a sample mean, so say X bar. So these 25 people, paid on average per month on public transit $125.80. Now we are not told what sigma is, but we are told in the objective that sigma is known. Alright, back if you look again. Alright, this is with population standard deviation known, right, up in the title of the objective. So if that's the case, right, if the population standard deviation is known, and we're looking at samples of size 25, and the averages, the means for samples of size 25, by the central limit theorem for means, the distribution of all these means for all these X bars for samples of size 25, because sigma is known, would be a approximately normal distribution with a mean called mu X bar and a standard deviation called sigma X bar, where the mean mu X bar, remember the mean of the means, the mean of the sample means was the mean of the population, mu. And from the null hypothesis, right, what we're going to assume that the null hypothesis is true, and then decide later whether or not we like that. Do we accept that statement or reject it? Do we accept this assumption or reject it? So we're going to assume here that the population mean is 140, and this will be the mean of the distribution of the X bars for samples of size 25. And the standard deviation, remember, of the X bars was the standard deviation of the population divided by the square root of n divided by the square root of the sample size. So now again, they didn't give us this, but we're told that it's known, divided by the square root of 25 here. And then from that we would find a test statistic. All right. So I'll draw a little picture. And here's a number line for different possible values of x bar, for samples of size 25, and we know this is going to be a normal distribution, right? So I draw a little symmetrical bell-shaped curve. And underneath the peak is the mean of all these x bars, which we're saying, we're assuming from the null hypothesis, we're assuming that that's 140. And again, we don't know the standard deviation. We're not told it. They just told us the test statistic. But how you would find, remember how you would find the test statistic is, the mean of these sample means is 140, we're assuming. Our sample mean, right, the sample she took, the average cost per month for public transit came in at $125.80. So that would be over here. Right, here's our x bar, or Rachel's x bar from the problem. And then the test statistic, remember the test statistic is when I convert these to z-scores. It's what's the z-score of our x bar, our sample mean. So then this distribution got normalized, right? It got changed to the standard normal. Right, so it got changed to the z distribution. Everything gets changed to their z-scores, so now the number line represents z-scores. Still a symmetrical bell-shaped curve, but now underneath the peak, remember the z-score of the mean is 0. And then our 125.8, I'll call this z-test. Now we are told, now remember how to calculate that. Now we don't know the standard deviation, but remember z-test is you take your sample mean, right, the value for our particular sample, subtract the mean of the x bars, which was 140 here, and then divided by the standard deviation of the x bars, which is that sigma over the square root of 25. Again, I don't know that. But we're told, right, we're told back in the problem that the test statistic is negative 0.52. Right, so this is negative 0.52. I'll write that on my little distribution here, sorry. And what this tells me, okay, this tells me that our sample, the sample mean earlier, 125.8, is negative 0.52. It is, a little more than half. It's 0.52 standard deviations below the mean. And that's not that far away. You're within 1 standard deviation of the mean, so you're pretty close. So because this is pretty close to the mean, I would say that assuming the mean is 140 isn't a bad assumption. If this was really far away from 140, like maybe more than 2 standard deviations, 3 standard deviations away, then I would say assuming that the mean is 140 is probably a bad assumption. Because if you assume the mean was 140 for the population, you would think our samples would be closer, if that truly were the mean. So that's what hypothesis testing is. You make an assumption, from the null hypothesis. You assume the equality, the null hypothesis, and you run through and decide if that's a good assumption or not. Will you accept that assumption or reject that assumption? All right, but now comes the p-value part. Now this all depends on what kind of a test you have. Now this goes back to I should have mentioned this earlier, I guess. This goes back to how the hypotheses are set up and what the alternative hypothesis looks like. See, the alternative hypothesis here is that the mean amount spent per month on public transit is less than some value. If that's the case, you're running what's called a left-tailed test. It's a left-tailed test. And if you're running a left-tailed test and you're doing this p-value approach, you're going to take your test statistic, right? So our negative 0.52 z-score here, and since it's a left-tailed test, I'm going to find the area to the left of your test statistic. All right, so the area to the left of the test statistic, and that is what's called the p-value of your sample, the p-value of your test statistic. All right, so again, this is in a left-tailed test. Right, in a left-tailed test. In a right-tailed test, the p-value is the area to the right of the test statistic. And in a two-tailed test, if your test statistic's left of the mean, your p-value is the area to the left of your test statistic times 2. Times 2. And in a two-tailed test, again, two-tailed, if your test statistic is to the right of the mean, your p-value is the area to the right of the test statistic, but then again times 2. Right, you're doubling these areas. But we only have a left-tailed test, so the p-value is simply the area to the left of the test statistic. That's what I call z-test. Now, you can find this in a couple ways. One is with the calculator, right? I've got a normal distribution here. So I'm pull the calculator up. TI 83, 84 are pretty similar. And remember how to find the area under a normal curve. Second, distributions. And then number 2, the normal CDF was to find the area under a normal curve. And then it says, okay, what's the lower value in this region that you're finding the area of? Well, there is no lowest value. So you see this value they've got right now, -1 times 10 to the 99th. That's some big negative number. Now I like to put in like -99999. I mean, that's not as big negative as the other one was, but that's just to indicate to me that there's no left value here. So some big negative number. And then what's the upper value in this region? That's our z-score of -0.52. And then mean 0, we're talking z-scores here, the standard normal, mean 0, standard deviation 1. And if you have an older one, you have to put it in this way, where you put the left value, comma, the upper value, comma, the mean, comma, the standard deviation. And this area, all right, so this area to the left of the curve is approximately 30%, 0.3015 if I go to 4 decimal places. Right. Now, another way you could find this is from a table. Now, they gave us a table back on the website here. So you remember this table? Your z-score tables, usually a z-score table gives you areas to the left, and that's what we're doing. We're doing a left-tailed test. So I look up my test statistic here. It's a z-score of -0.52. So -0.5, I'm in this third row down, and then 2, right, -0.52. So third row, third column in, and we're talking this area right here. So the area to the left of that z-score, the area to the left of our test statistic is 0.302. Now I said it was 0.3015, but if you rounded that to 3 decimal places, that would be 0.302, like they had on the table there. All right. Okay. Then you use the p-value to make a decision. Do you accept this assumption that the mean is 140, right? Do you accept the null hypothesis? You fail to reject it? Or do you reject the null hypothesis? Is my sample mean too far away for us to say that that's a good assumption for the mean, right? The mean of 140. So do you reject the null or not? So in this p-value approach, you compare the p-value to the significance level. You compare the p-value to alpha. Right? And if the p-value, and then here's how you make your decision, if the p-value is less than or equal to alpha, that would mean that your test statistic is in one of those rejection regions, right? If you were to go through the critical value method and set up, critical value in a rejection region, if your p-value is less than or equal to alpha, that would mean that your test statistic is going to be in one of those rejection regions. You're then going to reject that assumption that is made in the null hypothesis. We would reject the statement that the mean is 140. But if the p-value is greater than alpha, right, if the p-value is larger than the significance level, then that would tell us that our test statistic would not be in the rejection region. We'd be outside of it. So we would not reject, we would fail to reject the null hypothesis. We'd accept it. Right? So look here, our p-value is 0.302. Alpha was 5%, 0.05. And then which inequalities does this satisfy? Well, that is definitely greater than or equal to 0.05, right? 30% is definitely greater than or equal to 5%. Oh, I'm sorry, just greater than. Don't need the equal to. It satisfies this second inequality. 30% definitely greater than 5%. So we are going to, fail to reject the null hypothesis. We're not going to reject the null hypothesis. All right, so looking back at the hypotheses, that means we're keeping, right, we're keeping this and rejecting this. Right? One of them is kept, the other one is discarded, tossed away. So if we're keeping this, we're not rejecting our statement that the mean is 140. That means we're not supporting this statement, right? And this was the claim. Remember, the claim was that the mean was less than 140. We're not supporting it. Our evidence, our sample does not support. Right? We do not support this claim. And there you go. Right. Now going back here, they have you move some stuff around. All right. Now first, again, what kind of a test is it? It's a left-tailed test. So I move this dot here up to that part where, see, they have a rejection region and a critical value, but we're going to also be mentioning p-value here. So it's a left-tailed test. What was the significance level? Move that dot to 5%. You see again, it sets up our if we were doing the critical value method, the critical value would be a z-score of negative 1.645, and then this purple region here has an area of 5%. But now what's the test statistic, right? Well, they told us the test statistic was negative 0.52. So I move this to negative 0.52, and you can clearly see, come on, there we go. You can clearly see that the test statistic is not in this rejection region. Right, it's outside of it, so we're not going to reject the null hypothesis that the mean is 140. Right. And look at the p-value. Right. Again, for this left-tailed test, this p-value they're throwing up here is just the area to the left under the curve, the area to the left of our test statistic. And you saw on my calculator, you saw earlier, I have 0.3015, 0.302, right, up here. That's it. And then the p-value, you can very clearly see, is definitely greater than alpha. Right? The area of this purple region is alpha, is 5%. The area of the pink region is 30%. Definitely bigger. And if the p-value is greater than alpha, you're not rejecting the null hypothesis. Now, let's see here. Do not reject the null hypothesis because the absolute value of negative 0.52 is greater than 5. That's not the reason why. All right, it's because the p-value is greater than the significance level. That's why you're not rejecting the null hypothesis. So this fourth option down here. All right, and then there's probably a second part. Let's see, where they ask you to make a conclusion. Yeah. So use the information above. Choose the correct conclusion. Now remember, the conclusion should always be about the claim. And as you saw in my paper, right, the claim was that the mean was less than $140. We accepted, we didn't reject that the mean was equal to 140. So like I said, that means we're not supporting the claim. Right? The claim was in the alternative hypothesis. Now, if we rejected the null, then we'd support the claim. But we didn't reject the null. So we're not supporting the claim. So we would say, like, we don't have enough evidence to support the claim that the mean is less than 140. So there is not enough evidence, sufficient evidence to conclude that the average amount of residents per month is less than, well, 140, right? The claim was about 140, so not 125.8. Right, the 140, this one down here. There is not sufficient evidence to conclude that the average amount of residents spend per month on public transit is less than 140. That was the claim, and we're not supporting it, right? Because we didn't reject the null hypothesis. Great. And again, please read your answer explanations, right? Whether you're right or wrong. Read it when you're correct, just to make sure that your line of reasoning matches theirs, that actually is the correct reason you got it right instead of just guessing. And of course, if it's wrong, read the answer explanations. Hopefully you can figure out where you went wrong, so the next time you see a problem like this, hopefully you'll do better. All right. So that was a longer video, almost half an hour here, but again, taking you through the steps of a hypothesis test. And these steps I followed, a claim is made, you set up your hypotheses, and you can determine if it's a left-tailed, right-tailed, or two-tailed test. Then you find your test statistic from a sample, some z-score here. And then, with this p-value approach, then you find the p-value for your test statistic. All right, which will either be an area to the left or an area to the right, or an area to the left or right then doubled, right? If it's a two-tailed test, then you compare that p-value to alpha and decide if you're going to reject the null or not reject the null hypothesis. And then once you've decided that, then you can make your conclusion about the claim. Do you support the claim? Do you not support the claim? Same steps every time, though. All right, same steps every time. And it just depends on whether or not you're doing the critical value method or p-value method. Just a few things change, but you're pretty much doing the same steps every single hypothesis test. Alright, so hopefully this video helps you out when you're working on this kind of a problem on your own. And thank you very much for watching.